We're going to begin the course with an example of where we left off in Abstract Algebra 1. I'd like to do an example of another group action. So let X be the following set. I want to look at triples A0, A1, and A2. And A0, A1, and A2 are going to be in Z6. And I want to consider the triples such that if I add the three coordinates together, I get 0, and that's working mod 6. So I have a set X. If you want to write down some of the things in X, there's 0, 0, 0, 1, 2. And then if I have 1 and 2, and I need the three numbers to add up to 0, I guess I have no choice with the third component. It's got to be 3. What's another triple? Maybe 2, 5, and then if I have 2 and 5, I want them to add up to 0 mod 6. So I think I have to have another 5. No choice for the third component. So this is my set X. And I'm going to notice that Z3 acts on X by rotation. In other words, if I take like a generator for Z3, 1, and I operate on 1, 2, 3, then I'm going to cyclically shift everything to the right and get the element 3, 1, 2. So Z3 acts on X by rotation. Burnside's lemma tells us the number of orbits. This is where we ended with last quarter. We did a lot of examples with Burnside's lemma, counting the number of K colorings of the vertices of a cube or something like that. But in this case, the number of orbits is 1 over the size of the group, 1 over the size of Z3, times the sum over all elements in Z3, where I look at these sets. So 1/3 x0 plus x1 plus x2. If you remember from last quarter, these sets are the fixed point sets. So these are all the elements in X that are fixed when you apply 0. So how many elements in X are fixed when I add 0? So if I apply 0, I'm not rotating anything. That's the identity element. Part of the definition of a group action is the identity element changes nothing. So the size of this set is actually the size of X itself. Now, when I was forming this set X, you may have noticed that the first two choices were free, but then my third choice was fixed upon me due to this condition. So I actually have 6 choices for the first component and the second component, but after I make those independent choices, the last component is dictated already. So there are actually 36, 6 times 6 elements in X. Now X1, this is the fixed point set. Let me remind you what that is. So the fixed point set, X1, that's the set of elements A0, A1, A2, such that if I rotate once, I get the same triple back. So 1 plus A0, A1, A2 is itself. What kind of triples are the same when you rotate cyclically? Well, this is just the set of everything of the form AAA, where A plus A plus A is equal to 0. This is actually the same as the set x2. So I could say the same thing for x2. x2 and x1 have the same number of elements in them. So I can write this as 2 times the size of this set x1. We're going to simplify this in a minute, but I'm going to notice now that 36 is divisible by 3. So in order for this to be a whole number, which it needs to be, it's the number of orbits, so in order for this to be a whole number, I need x1 to be divisible by 3 as well. So I'm going to make a note here. Note, this implies that x1 is divisible by 3. That's actually the idea we're going to use in a minute when we generalize this example. Okay, but anyway, so I get 1/3, 36 plus 2, and then how many elements in Z6 are equal to 0 in Z6 when I add them to themselves 3 times? So if you think about it, A could be 0, 2, or 4. There are only 3 options here. So the final answer is 14. There are 14 different orbits when Z3 acts on X by this rotation move.